Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over part 4 of our work on applications of differentiation, problems 11 to 15. This problem should prepare you for problems 11 to 15 of chapter 3, section 1 of the Larson AP Calculus textbook. The instructions for the problems we are going to be doing are for you to identify the critical numbers of the functions given below. Okay, let's start with problem 11. Let's say we have the function f of x equals 2x to the third minus 4x squared. So the task is to identify the critical numbers. So how do you find critical numbers? The critical numbers are where the derivative is equal to 0 or the derivative does not exist. Alright, so that's what we're going to be doing. So let's go ahead and take a look at this function. We have f of x is equal to 2x to the third minus 4x squared. So to see where it's the derivative is 0 or non-existent, we have to differentiate and set it equal to 0, the numerator and denominator. So first thing you want to notice is that this is a polynomial function, so that tells you that it's smooth and continuous everywhere in the domain, which means that there isn't any point on this function where you have a non-existent derivative. Okay, so f prime of x equals dne will not be applicable or is not applicable to polynomial functions. That's just something to keep in mind. Alright, so let's go ahead and differentiate that using our differentiation rules. We're going to differentiate them term by term. F prime of x, if you differentiate the first term, 3 times 2 is 6. X to the 3 minus 1, that's 2, minus 2 times 4 is 8x. So that's the derivative of the original polynomial function, the cubic binomial we have here. So what we want to do now is we want to find where the derivative is equal to 0 and where it does not exist. Alright, so whenever you want to find where the derivative is equal to 0, you just basically take the numerator. Well, that is the function, so 6x squared minus 8x equals 0. So let's solve this equation, this quadratic equation. We can factor out 2x. Factor out 2x, you have 3x minus 4. And then you set the factors equal to 0 using the zero product property. You have 2x equals 0 and 3x minus 4 equals 0. So if we solve this, divide both sides by 2, you have x equals 0. And then here you can add 4 and divide by 3. You have x equals 4 thirds. Now to find f prime of x equals dne, you just basically extract the denominator component of your function. This is a polynomial function, so we do not have a denominator component, which basically tells us that the derivative is always defined. So f prime of e equals dne. What number satisfy that equation? Well, no value for this particular function satisfies this condition. Okay, so that ends the story for us. We now know what the critical numbers are. The critical numbers are x equals 0 and x equals 4 over 3. So that's the answer to question number 11. Alright, let's take a look at question 12. So let's say we have f of x equals 1 over 8x to the fourth minus 1 over 16x squared. So we want to find the critical values. Okay, So critical values are where the derivative is equal to 0 or non-existent. So let's go ahead and find the derivative first. F prime of x. F prime of x equals 4 over 8 x to the, you mark this power down by 1, so 3 minus, and then here we have 2 over 16. Applying the power rule for differentiation, times x to the first power when you subtract 1 from the 2. Let's simplify that. F prime of x is going to be 4 over 8 reduces to 1/2 x to the third minus, if you reduce this part here, 1/8 x. Now we have the derivative. To find the critical numbers, we're going to look for where the derivative is equal to 0 and where the derivative does not exist. Okay. Now this function is also a polynomial function. Don't let these fractional coefficients deceive you or distract you. This is a polynomial function. Okay. We're just focusing on the powers of the variables, making sure that they are positive. They're integers, basically. So now let's go ahead and see the first condition where the derivative is equal to 0. So you just take your derivative, 1/2 x to the third minus 1/8 x, set it equal to 0, and solve. Okay. So let's see what we can do here. We can factor out 1/2 x. So factor out 1/2 x, and then you're left with x squared minus. Now, what do you get when you factor out 1/2 from 1/8? You can just reverse engineer the answer. So you ask yourself, 1/2 times what gives you 1 over 8? 1/2 times 1/4 gives you 1 over 8. Okay, another way you can do it is you just say, okay, what is 1 over 8 divided by 1 over 2? And then you drop, change, flip, 1 over 8 times 2 over 1, and then your answer is 1 over 4, because 2 goes here 1 and 2 goes here 4. So whichever way you want to approach the problem, you will get 1/4 as a result of dividing 1/8 by 1/2. Alright, let's proceed to use the zero product property. We're going to set 1/2 x to 0 and x squared minus 1/4 this quantity to 0 also. This can simply be solved by multiplying both sides by 2. You just double both sides of the equation, and you have x equals 0. So that's one of the critical numbers. We can factor this or solve and use the square property. Let's factor it out. So to factor this, we just root the first term and the second term, and then express it as a sum and difference. We're using this approach because we have a difference of squares. Okay, so remember, if you have a difference of squares, you can always factor it. So the factored state here is x minus 1/2 times x plus 1/2, because the square root of 1/4 is 1/2. Using the zero product property, we have x minus 1/2 equals 0 and x plus 1/2 equals 0. And then when you get x isolated, x equals positive 1 over 2 and x equals negative 1 over 2. Okay, so where is the derivative non-existent? Well, we have a polynomial function. We don't have any funny things happening with the polynomial function. Okay, the derivative is defined at every point in the domain. So f prime of x non-existent where? Nowhere. Alright, so we have our critical numbers. Our critical numbers are x equals, let's put them in order, negative 1/2, 0, and 1/2. Those are our three critical numbers for the function in question number 12. Alright, let's take a look at question number 13. Now let's say we have the given function g of x equals x times the square root of 3 minus x. Okay? Alright, so we want to find the critical values, basically where g of x, g prime of x is equal to 0, or where it does not exist. Okay, so find critical values, critical numbers. Basically, you're looking for where, in this particular case, g prime of x is equal to 0 or g prime of x does not exist. Alright, so let's see what we have here. We have our function x root 3 minus x. We have a product of a radical function and a linear function. So we're going to have to use the product rule here. There's no way we can avoid using that. No manipulation will result in avoiding that procedure, so we have to use it. Alright, the first function is u, and the second function is v. So the derivative, if we want to differentiate the function g prime of x, is going to be x root 3 minus x prime. Alright, so we have uv, u times v prime. So what is the product rule? Product rule is as follows. U times v prime is vu prime plus uv prime. Alright, so we're just going to go v, which is the square root of 3 minus x. So that multiplied by the derivative of x, which is 1, plus u, which is x, multiplied by the derivative of root 3 minus x. So that's we're gonna have to use the chain rule here. Okay, if we differentiate this using the chain rule, we're going to have 1 over 2 root 3 minus x times negative 1. Okay, how did that happen? Well, let's show the work on the side here. So we have a little scratch work. We want to find the derivative. Let's just call that f. Okay, f of g of x is equal to x. No, is equal to the square root of x minus 3, or 3 minus x. Alright, so we're going to use the chain rule because we have a composite function, the composition of a radical and a linear function. So we're going to call the outer function f. F is going to be root x, and then the inner function g is going to be 3 minus x. Okay, differentiate both of them. F prime is going to be 1 over 2 root x, and then g prime is going to be negative 1. So if we apply the chain rule of a composite function, is basically f prime of g of x times g prime of x. So if we do that here, we're just going to simply plug in g into f prime. That'll give us f prime of g of x, and multiply that by g prime of x, which is negative 1. Alright, so the derivative will be 1 over 2 root 3 minus x times the derivative of the inner, negative 1. Alright, so that's how we got this particular result right here. Okay, let's go ahead and simplify our derivative. G prime of x is the square root of 3 minus x plus, actually we have a minus there, so minus times plus is minus, so minus x over 2 root 3 minus x. Alright, now let's go ahead and combine these two fractions. Now this is the goal. We want to express this fraction as a quotient of two functions. Why? Because the numerator will help us determine where the derivative is equal to 0, and the denominator will help us determine where the derivative is non-existent. Okay? When you have a 0 denominator, the function is undefined because you cannot divide by 0 to yield a defined output. Okay, so that's the strategy here. So we have to combine them so we can be able to find those results. So put this over 1. We now have to find the LCD of these two denominators. The LCD of 1 and 2 root 3 minus x is 2 root 3 minus x. So in order to make the denominators identical, we'll simply multiply this fraction on the left by 2 root 3 minus x on the top and on the bottom. Okay, if we do that, times it on the top, times it on the bottom, we're going to have g prime of x will now be, now in the numerator, if you multiply 2 root 3 minus x and root 3 minus x, you have root 3 minus x quantity square. So the square and the square roots cancel out, so you just have 3 minus x. Okay, you have that. And then this over 2 root 3 minus x minus, this is unchanged, 2 root 3 minus x. And then you can combine it further. You can distribute the 2. And then that gives you 6 minus 2x. And then minus x. Now, since the denominators are the same, we can just combine them into one fraction. Okay? Over 2 root 3 minus x. And then you're now going to have 6 minus 3x over 2 root 3 minus x as your derivative. Alright, so we found g prime. Now what we want to do is we want to find where g prime is equal to 0 and where it's non-existent. So to find where it's equal to 0, where is g prime of x equal to 0, we just simply extract the numerator. Okay, why do we do this? If you set the entire function equal to 0 and you cross multiply, the denominator component is gone. Alright, so you can just take the numerator and set it equal to 0. Alright, let's solve this for x. Subtract 6 from both sides and then divide by, subtract 6 from both sides, this becomes negative 6. And then you divide by negative 3 and you have x equals 2. Alright, so that's one of the critical numbers. Now let's go into where g prime of x does not exist. One thing I didn't state earlier is the domain restriction on the original problem. So this is where x is less than or equal to positive 3. Alright, so we have restrictions on this function. Alright, that's just by the way. Okay, so to find where the derivative is non-existent, what we'll do is we'll take the denominator and set it equal to 0. Okay? Now you can divide both sides by 2. That gives you root 3 minus x equals 0. And then you can square both sides of the function, the inverse of square root, and you have 3 minus x equals 0. And then you can add x to both sides and switch your equation around, and you have x equals 3. Okay? So there goes the other critical numbers. So our critical numbers for this problem, critical numbers are x equals 2 and x equals 3. So there you have it. Alright, let's take a look at question number 14. Now let's say you have the function f of x equals 3x over 2x squared minus 1. We want to find the critical values or critical numbers. Basically, you're looking for where f prime of x is equal to 0 or f prime of x does not exist. Okay? So let's start out by finding f prime of x. So we have the function. The function is a quotient of two functions. So we might have to use the quotient rule, but let's not be in a haste to do that. Let's see if we can rewrite it in a way that avoids the use of a quotient rule. And there's nothing we can do here to avoid that, so we have to use the quotient rule. Okay, so f prime of x is equal to 3x over 2x squared minus 1 prime. So what we have here is the numerator is u and the denominator is v. Okay, so what is a quotient rule? If you have u over v and you want to find the derivative, u over v prime is equal to vu prime minus uv prime divided by v squared. Okay, so let's apply that procedure here. F prime of x is going to be v, which is 2x squared minus 1, vu prime. I'm going to write down the intermediate steps so no one gets confused. Minus u, which is 3x v prime, 2x squared minus 1 prime. So that's vu prime minus uv prime, divide the whole thing by v squared. Okay, which is 2x squared minus 1 quantity square. Okay, let's go ahead and simplify the numerator. F prime of x is going to be 2x squared minus 1. 3x prime is just 3 minus 3x. 2x squared prime is just 4x because the derivative of 1 is 0. Divide that by quantity 2x squared minus 1 squared. Okay? Alright, let's simplify further. Distribute the 3. You have 6x squared minus 3. And then minus 3x times 4x is minus 12x squared. And that whole thing divided by quantity 2x squared minus 1 squared. We can combine 6x squared and negative 12x squared. Like terms, it gives us negative 6x squared minus 3 divided by 2x squared minus 1 squared. Ladies and gentlemen, we have our derivative. Okay, let me just rewrite it over here. F prime of x equals negative 6x squared minus 3 divided by quantity 2x squared minus 1 square. Okay, so let's go ahead and find the critical numbers. We're going to look for where the derivative is equal to 0 and where the derivative is non-existent. Okay, let's do where the derivative is equal to 0 first. Do you know what we extract here to accomplish that? We take the numerator, okay, so negative 6x squared minus 3 is equal to 0. Let's solve this. Negative 6x squared, you add 3 to both sides, equals 3. Divide both sides by negative 6. And that yields x squared is equal to negative 1/2. And then to get x isolated, you take the square root of both sides. And then you have x equals, anytime you take the square root of a square, you introduce plus or minus, and then you root in a negative number. I is the square root of negative 1. plus or minus I root 1 over 2. Okay? You can simplify that further, but we can stop here because this is non-real. It's not real. Imaginary numbers do not qualify as critical numbers for a function, okay? So this tells us that there are no points on the graph where the derivative is equal to 0, okay? Alright, so this part has failed us. Let's go to the DNE component. To do that, we're going to extract the denominator, 2x squared minus 1, and set it equal to 0. Okay, let's just put a side note here. Denominator equal to 0. And then here is where you do the numerator equal to 0. Alright, so to solve this, you add 1 to both sides. 2x squared equals positive 1. Divide both sides by 2. X squared equals 1 over 2. You can take the square root of both sides of the equation. So we're going to have x equals plus or minus 1 over root 2. Of course, we want to rationalize the denominator, root 2 and root 2. And then we have our two critical numbers, plus or minus root 2 over 2. Alright, so let's go ahead and write it down. Our critical numbers are x equals negative root 2 over 2 and positive root 2 over 2. Okay, so those are the answers for question number 14. Let's go ahead and box that. Alright, let's take a look at question number 15. We want to find the critical numbers of the function g of x equals cosine square x minus sine x. Okay? Alright, so to find the critical numbers, what do we do? To find the critical numbers, you're basically looking for where f prime of x is equal to 0 or where f prime of x does not exist. Okay? Alright, so let's go ahead and find the derivative of this function. So g of x is equal to cosine square x minus sine x. Now, to find the derivative, we have to be careful with this cosine square x business. Okay, let's write it in a form that makes it easy for us to accurately apply the right procedure. Alright, so cosine square x is basically the function cosine x square. Alright, so we are differentiating that, term by term differentiation minus the derivative of sine x. So anytime you have a trig function written in this format, please rewrite it in a way that makes the composition of the functions explicit so you do not make errors in the application of the chain rule. Alrighty? So we have it written out clearly for us. So if we want to find g prime of x, let's do some scratch work here with the chain rule process. So scratch. We have a composite function, f of g of x is cosine x square. So we want to find the derivative of that. So the outer function f is the quadratic x squared. The inner function g is cosine x. Differentiate both of them, f prime of x. Let's just call it f, f prime. So f prime is 2x. And g prime is the derivative of cosine is negative sine. Alright, so if we apply the chain rule, derivative of the outer evaluated at the inner times the derivative of the inner. So the derivative of f of g of x is going to be 2 cosine x times negative sine x. Okay, so you can put a minus here and just put a sine x here. So that's what the derivative is. So let's apply that here, insert it into the derivative of g. So we'll have the derivative of this is negative 2 cosine x sine x. Applying the chain rule. And the derivative of sine is cosine, so we have negative cosine x. So we have g prime. Now one thing to note about this function here is that the sine and cosine functions are smooth and continuous. You don't have any discontinuities, cross corners, or vertical tangents with the sine and cosine. So when we have the product, sum, and difference of those functions, is going to inherit the same domain. Alright? But when you have the quotient of any of these functions, then you have a totally different story. In this particular case, we do not have any denominators, so what we'll expect is a scenario where the function does not have any points where the derivative is non-existent. So our focus here will just be on where g prime of x is equal to 0, because it's smooth and continuous. Alright, so let's go ahead and do that. So what we're going to do is take the function. Another way that can help you determine if you have places on a trig function where you have non-existent derivatives is try and rewrite all your functions as a combination of sine and cosine only. If you do that and you find out that you have a function in the denominator, then you know that there are points on the graph where the derivative will not exist. Okay, so what am I talking about? Let's say you have secant in the mix, for example. Secant is one of a cosine, so whatever cosine is equal to 0, you have a discontinuity, which means the derivative does not exist there. So we don't have any scenario here where sine and cosine is in the denominator, so we know that we are good to go. Alright, set this equal to 0. So we're going to solve this equation, this trig equation. Start off by factoring out the greatest common factor. Cosine is common to these two terms that have been subtracted. So we can factor out cosine. Also, we have a negative common here, so we can factor out negative cosine x, and that leaves us with 2 sine x minus 1. Now using the zero product property, we have negative cosine x equals 0, and 2 sine x minus 1 equals 0. Alright, so here for the first one, just divide both sides by negative 1 and you have cosine x equals 0. So to get x, you're basically looking for the inverse cosine of 0. Okay? And then let's put a domain restriction on our problem here, or else we have infinitely many critical numbers. So let's say we're looking for the critical numbers on the domain from 0 to, let's say 0 to pi over 2. Alright? Included. Bam. Alright, so with that in mind, let's solve this equation. So to solve this equation, cosine x equals 0, or the inverse cosine of 0, in the domain that we were given, what x value would you get? Use an output or an answer of 0 when you take the cosine. To do that, you can use a unit circle, or you can use the trig function, the graph of cosine. Let's use a unit circle first, and then we'll use the graph to do that. Okay, so this is another scratch work. We're looking for the angular value that gives us 0 when you take the cosine of it. Okay, so cosine of what is equal to 0? That's the question. Alright, so we're restricting our angular domain to be between 0 and pi over 2. So the first quadrant including the axis, okay? So you gotta remember what the two coordinates signify. Cosine is the x coordinate and y is cosine is x and y is sine. Alright, so here, starting from this point on the unit circle, this is 1, 0. Okay, so for 0 degrees on the unit circle, cosine is 1. We're looking for the degree value that gives us 0. But when we go full circle over here, this is 0, 1. This is your cosine right here. Bam. So cosine of what gives us 0? What's the angular measure from here to here? That's pi over 2. Alright, so this basically helps us to see that x is equal to pi over 2. Cosine of pi over 2 is 0, or the inverse cosine of 0 is pi over 2. If you wanted to use the cosine curve, that's will work also. So you just sketch your cosine curve. It looks like a nice little cup. I'm just going to go all the way to pi over 2 because that's the restriction on our domain. So there goes your cosine graph. Alright, so the question is what angular value, so this is, well actually I went past that. I went all the way to pi. This is pi right here. So this is pi over 2. So what does this graph help you to see? It helps us to see that cosine of pi over 2 is 0. So consequently, the inverse cosine of 0 is going to be pi over 2. Alright, so x is equal to pi over 2. That's the solution to the first equation. And then the second one, we just add 1 to both sides. We have 2 sine x is equal to 1. And then divide both sides by 2. Sine x is equal to 1 over 2. Okay, so here to solve this, we're going to ask ourselves, sine of what angle between 0 and pi over 2 is 1/2? Okay, that's the same thing as finding the inverse sine of 1/2. So let's use the unit circle for this one. It's much better to use the unit circle for this particular problem. So we know that sine is the y coordinate, right? Y sin, when it can be good, right? So y is for sine. We're looking at the first quadrant, so let's put in our points. Here is 1, 0. We have 3 points in the quadrant, 1, 2, 3, and then the last one is we achieve reversal, 0, 1. Okay, so before 1 is root 3 over 2, and that always goes with 1/2. Positive, and then in the center they are both identical, root 2 over 2, root 2 over 2. And then over here, you just switch these two around, 1/2 root 3 over 2. Okay, so this is 0 degrees, this is pi over 6 radians. Why am I switching between radians and degrees? Let's just stick with radians, okay? Alright, so 0 radians, pi over 6 radians, pi over 4 radians, pi over 3 radians, and this is pi over 2 radians. So the question is, which of this radian angular values has 1/2 as the y coordinate? Okay, we're focusing our attention on the y coordinate, and we can clearly see that it is pi over 6, or 30 degrees. Okay, so sine is y, so this one right here is sine theta, that's the y coordinate. And then our target value is 1/2, so this has 1/2, so our answer is going to be pi over 6. So x is equal to pi over 6. Alright, so there goes our critical values, but we're not completely done yet. We also have to find where g prime of x does not exist. And as indicated earlier, there is nowhere that this is applicable since it doesn't have any denominator components that can achieve a 0 value, thus resulting in an undefined output. Alright, so our critical numbers are x equals, let's put it in ascending order, pi over 6, and x equals pi over 2. So those are the answers for question number 15. Thanks so much for taking the time to watch this presentation. I really appreciate it. If the contents of this tutorial helped you in your studies of the applications of derivatives, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions or comments, just place it in the comment section below and we'll be more than glad to support you. Don't forget to subscribe to our channel for updates to the remainder of this prep series for AP Calculus. A lot of tools and prep resources can be found on mathgotserved.com under AP Calculus. Thanks again for watching and have a wonderful day. Goodbye.